Welcome to my YouTube channel. Today I will lecture start with MSc Part 1, Semester 2, Paper 4, Unit 1st, Chromatography. Then first of all, the explain with a gas chromatography. There are gas solid chromatography and gas liquid chromatography. It means gas solid chromatography, they involves the solid plus gas, and then gas liquid chromatography, then liquid plus gas. Then this is adsorption, and next is partition. Then theory of the gas chromatography, they are studied in the instrumentation parts, and then next part is the application part. Okay, then again classify into the gas chromatography with the partition chromatography, paper chromatography, gas liquid chromatography, and HPLC. HPLC, that means high performance liquid chromatography. Okay, then the in short part in the gas chromatography, the principles of gas chromatography. Then again divided into two parts. Then GSC adsorption, and second part is the GLC partitions. And then a most volatile, be less volatile, and least volatile separation technique, they can be used in this gas chromatography technique. Then main points of this gas chromatography, the principle of the gas chromatography. Then gas chromatography consists of a gas as a mobile phase and stationary phase, may be solid or liquid. The time required for the separation of a component is decided by a large number of factors, but it primarily dependent on extent of adsorption of solute in GSC or its partitions in liquid phase and gas mobile phase in GLC. If the solute shows more affinity for solid surface or liquid stationary phase, it will take more time to move over the entire length of the column, and that it will take more time for separation and vice versa. Consider a small length of a column. Sample contains three components A, B and C is rejected from sample injection port, and it will be carried by mobile phase in the column. In the column, the sample is get vaporized and the most volatile component will separate out first, whereas least volatile component will separate out later on. Then next, the distribution coefficient shows the distributions of the molecule of the solute in two phases. K is equals to, K is the universal constant, K is equals to concentration of a solute in the stationary phase divided by concentrations of solute in the stationary phase. Stationary, not mobile phase. A smaller value of K means that a concentration of a solute in mobile phase is more. It will require the less time to come out from the column. Other hand, a larger value of K means that concentration of a solute in stationary phase is more. It will require more times to come out from the column, and the time required to elute the solute component from the column is called as the retention time, and it's a characteristic of every species. Qualitative analysis can be performed using retention time. Quantitative analysis can be performed from the area of the peak is calculated from the peak. And this is the graphical representation of this volatile compound. In the operations of the gas chromatogram, the solutes in a mixtures are completely vaporized in the injection port, and they are moved through the column by a carrier gas under pressure, and it is in the column where separation takes place. From the column, the separated solute pass through the detector where they are sensed, generating an electronic signal, and the signal is then amplified and normally displayed on the strip chart recorder. The trace plotted on the recorder is called a chromatogram. It is a plot of the detector response, a millivolt as a function of time. Usually time is a abscissa and millivolts the coordinates. From the chromatogram, several general observations can be made. Under a given set of experimental conditions, each peak has a characteristic retention time and retention volume that are useful in qualitative analysis of a solute. The first definition is a retention time, that means TR. It is used for qualitative analysis, and it is defined as the time between the point of injection of sample and appearance of the solute peak at the detector. And other definition in the retention time, the time required to elute the solute component from the column. The retention time is equals to length of column packing divided by velocity of the solute. Next concept is the retention volume, that means VR. It is used for the qualitative analysis. Volume of mobile phase requires to elute the solute component from the columns is called the retention volume. Retention time and retention volume are related by equation VR is equals to TRF, where F is the flow rate of mobile phase. Then the formula of the retention volume is equals to length of column packing divided by velocity of the solute. Next concept is the relative retention. It is defined as the ratio of the retention time or retention volume for the substance after correction for Tm and Vm to the corrected retention time or retention volume of a reference compound. Whereas Tr is equals to retention time of the substance, Tm is equals to retention time of the mobile phase, Tref means retention time of reference compound, Vr is equals to retention volume of the substance, Vm is equals to retention volume of the mobile phase, V reference is equals to retention volume of the reference compound. Next, height equivalent to theoretical plates. Efficiency of column depends upon number of theoretical plates that columns is supposed to made. HATP is the length of column corresponding to a single theoretical plate is equals to L upon N, where L is the length of column, N is the number of theoretical plates. An efficient column is one for which N is large or H is small. Next is the peak resolution. What is the peak resolution? Then resolution is the measure of separation between adjacent peak in chromatogram. As the difference between the retention time of the peaks increases, the separation increases. That is, resolution is directly proportional to the difference in retention time of the peaks. Then R is equals to 2 into TR2 minus TR1 upon W1 plus W2. Whereas TR1 and TR2 is the retention time of two peaks and W1 and W2 are width of two peaks. Then in shortly instrumentation part of the gas chromatography. Then how it's working of the gas chromatography instrumentation. In the operation of a gas chromatograph, the solutes in the mixtures are completely vaporized in the injection port and they are moved through the column by carrier gas under pressure. It is in the column where separation takes place. From the column, the separated solute pass through the detector where they are sensed, generating an electronic signal. And the signal is then amplified and normally display on strip chart recorder. The trace plotted on the recorder is called the chromatogram and it is plot of the detector corresponds in millivolts as the functions of time. Usually time is the abscissa and millivolts the coordinates from the chromatogram. Several general observations can be made under a given set of experimental conditions. Each peak has a characteristic retention time and the retention volume that are useful in qualitative analysis of gas chromatography. The next point is the properties of selected gas chromatography. Then what is the detector they can be used in the gas chromatography? That first detector they can be used in this gas chromatography, thermal conductivity detector. Second is the flame ionization detector. Third is the electron capture detector. Fourth, flame photometric detector. Fifth, nitrogen phosphorus detector. Sixth, photoionization detector. Seventh, Hall detector. Eighth, mass spectrometer. And last is the Fourier transform infrared. Then this is the first example of this detector is the flame ionization detector and they are working in this figure. What is the principle of the flame ionization detector? The principle of the flame ionization detector is organic compound when reaches to the flame, produce ionic spaces that conducts electricity through the flame. Hydrogen is a carrier gas in this detector. In FYD, the eluents coming from the column is combines with hydrogen and air to form combustible mixture. This mixture forms a flame which provides sufficient energy from ionization, and the gaseous cations from a flame are attracted to negative electrode and repelled by the positive electrode. Upon striking the collector electrode, the positive ion causes a current to flow in an external circuit. The current flow is proportional to the concentrations of ionizable sample component. What are the limitations of this flame ionization detector? They are the first limitation is the flame ionization detector responds to only ionizable substances. Second limitation, it does not respond to inorganic compound containing nitrogen gas, oxygen gas and carbon dioxide gas. Third limitation, it destroys the sample entered into the flame. Next detector is the thermal conductivity detector. They are the instrumentation part in this figure is shown that they are how it's working in this figure in thermal conductivity detector. The thermal conductivity detector is based on the difference between thermal conductivities of the pure gas and carrier gas containing sample. Thermal conductivity detector consists of two identical brass cells fitted with platinum or tungsten wires, and these resistance wires consist of reference and sensing elements which forms two arms of Wheatstone bridge. Both these wires are heated by an electric current when pure carrier gas flows through both the cells, and the temperature and hence resistance of both the filaments are in Wheatstone bridge is same. We show that the balance circuit. When column effluent allows to flow through one cell and pure gas through the other cell, the resistance of both wire changes due to the unequal cooling, which results in increase in current. This current is directly proportional to the quantity of the solute present in the sample. There are the many advantages of this thermal conductivity detector. They can be first advantage is it responds to organic and inorganic substances. Second, it's non-destructive detector. The solute after separation can be collected. And third, it's simple and gives large linear dynamic range. The basic principle of electron capture detector is based on electron absorption by compounds having an affinity for free electrons. It responds to compounds having an electronegative element or functional group. Methane gas is used in this detector because it easily undergoes ionization. In ECD, NiH6 foils is used as a source of beta rays. In presence of beta rays, carrier gas undergo ionization and this form positive carrier gas ions and electrons. The electrons emitted during ionizations are captured by positive collector electrode. When a sample component enters the detector, electrons emitted by the carrier gas are captured by the component, and the net result is removal of electrons from the system and decrease in standing current. The decreased current is recorded as negative peak on the recorder. Third detector is the electron capture detector. They can be moving in this figure and how it's working in this gas chromatography. The first advantage of the electron capture detector, it responds to compounds that capture the electrons. Second, organic compounds containing electronegative groups, for example nitro groups, phosphorus, oxygen and halogen. Third advantages, ECD is a very good detector for insecticides, pesticides, polychlorinated biphenyls. And fourth advantages is it is non-destructive in nature. Then next part is the application of the gas liquid chromatography. There can be first application is a qualitative analysis, second quantitative analysis, and third application in various fields. Then first application is the quantitative analysis. The chromatogram obtained on the recorded chart can be used to measure quantitatively the concentrations of component in a mixture. In general, three methods are used for the quantitative evaluation. First is the area normalization method. In this method, it is assumed that the entire sample is eluted from the column and the area of each peak is measured, and percentage composition is obtained by the dividing the individual peak area by the total area of all the peaks and multiplying by 100. The values obtained will be acceptable only if the detector response is the same and for all the components of the mixture. If not, the detector response factors for each component needs to be established and appropriate correction made in the measured areas. Second is the internal standardization method. In this method, known amount of sample and standard are mixed and chromatographed. The peak areas for the sample component and for standard are measured and ratio of the both peaks areas are determined. Other area ratio are plotted against weight ratio to obtain a graph. Chromatograph area ratio for unknown are compared directly with those for the known amounts. Thus, accurately known quantity of the internal standard is added the unknown sample, and this mixture is chromatograph and area ratio are measured. The requirement for a suitable internal standard are summarized as follows. The standard must be compound, which is well separated from all components of the mixtures being analyzed. Second, the standard must not be react with any component of the sample, nor it should influence the physical properties of the other component, for example, volatility. Third, it should yield a symmetrical chromatographic peak. It must be chemically similar to the unknown compounds. Third is the comparison method. In this method, a synthetic mixture containing known quantities of the component of interest in the range of concentration expected in the unknown sample is prepared and analyzed. The values for the peak area for a different known volume of a synthetic blend are estimated and calibration curve is plotted. An exact quantity of the unknown sample is then injected and the peak areas so calculated are used to read from the calibration curve, and the concentrations of the component in the unknown mixture is then determined. Then the applications of the various field in the gas chromatography. The first application is the bacterial identification. Long chain fatty acids found in the bacterial cell can be used to distinguish between various microorganisms. Fatty acids with chain length from C10 to C20 can be separated and estimated on the 3-meter glass column of 2 mm internal diameter pack with 3% Sp 2100 DOH at oven temperature at of 150 degrees Celsius to 225 degrees Celsius with nitrogen gas at flow rate of 20 ml per minute. Second application is environmental analysis. Water analysis. The organic pollutant in water are concentrated from water samples by solvent extraction or by purge and trap technique. The volatile pollutant are analyzed on 80 divided by 100 mesh Carbovax 1500 columns. Air analysis. The analysis of organic vapors in the industrial area. Environment for the assessment of exposure to workers is done as follows. First is the organic vapors are collected on the charcoal adsorbent with a portable pump. Second, desorption from charcoal is done is closed with carbon disulfide. And third, analysis of the desorbed sample is done on gas chromatography using 6-meter 3 mm internal diameter S column pack with 10% Sp 1000 by temperature programming from 100 degrees Celsius to 200 degrees Celsius. By this method, pollutants such as the vinyl chloride, xylenes and aromatic hydrocarbons can be estimated. Second, clinical and toxicological analysis. Toxicologists have recognized the usefulness of gas chromatography for the analysis of the toxic substances. The analysis of the lidocaine and diphenylhydramine has been done using the flame ionization detection. Next is the forensic toxicology. Is a highly specialized branch of analytical chemistry concerned primarily with analysis of specimens from different organs of the human body for toxic substances. A simple gas chromatography system utilizing four columns and three liquid phases, complemented by a direct solvent extraction stream designed to detect common poisons, drugs, and human metabolites to a sensitivity limits of 2 microgram per ml in blood, urine, and tissue is developed. Thank you.